With a 5-year, $20 million grant from the National Science Foundation, the University of Wyoming is researching climate impacts on the nation's key headwater regions. And the first focus is the Snake River Headwaters. So would like to introduce Dr. Brian Schumann. He's Wyoming Excellence Chair in Geology and Geophysics at the University of Wyoming, and he's also the principal investigator of the $20 million National Science Foundation grant. So please welcome Brian.
Thank you, Megan. And thank you all for being here and for the opportunity to come talk with you. I am going to try to give you a bit of a primer, a sort of short overview of how climate change is something that's also part of the equation here that's worth thinking about, because climate change is really water transformation, and that's something that is already impacting this region, but certainly is something to consider if you're planning infrastructure or any kind of plans that are going to last for hopefully decades. This water transformation that's upon us is something that's really important to plan into that. And I can't stress enough, it was fascinating listening to the previous panel. I am originally from New England. I spent a lot of time, and even still in my life, in Connecticut and Rhode Island and Massachusetts, out in Cape Cod, in different communities where I've seen these septic systems just totally transform the water. And what I want to talk to you about is how climate change is just another transformation that's added to this and adding to the challenge. And so I'm just going to try to give you this kind of broad perspective on what's changing here and what we can expect in the future, and how we have to keep those changes in our mind when we're planning for the future. And of course, we've seen this last year was such a great year for demonstrating the types of things that are on the radar here. And it's not as simple as things are just going to get drier or they're just going to get wetter. We saw last year how Jackson Lake was drawn down tremendously, and at the same time Red Lodge had these unbelievable floods. And so that is kind of an illustration of how the changes in the future are not necessarily simple, and they are complex issues that we have to consider. So I hopefully you can see this great photo from Ansel Adams from 1942, the classic photo of the Snake River. I love this as a starting point. You kind of look back to 1942 and think, how much has this photo changed? How much does this landscape change? How much has that water changed in that time frame? And you can also try to project out how different might it look in 2042. That's not that far down the road, and that's certainly the time scale in which infrastructure and things that policies that we hope to have in place will get played out. And so what do we want this to look like in 2042? And what are some of the changes that are taking place, and what are the consequences that we'll face with that? Now, the greatest uncertainty about the future in terms of our climate is not the physics of how we understand the climate system. The greatest uncertainty, and there is a great deal of uncertainty, it's not that will it warm or not. We are certainly doing things to the climate system that are causing it to change, but the greatest uncertainty is what we sort of collectively decide globally as to how to manage the pollution of carbon to the atmosphere. And so just to help you think for a moment here, this graph is just showing how since 1900 out to 2100, how the amount of carbon dioxide has changed in the atmosphere, but a wide range of possible futures where it could continue to change. And if you want to warm up for a moment here, I've got some climate physics fitness exercise for you to help you. So if you don't understand why greenhouse gases make the world warmer, it's really simple. It comes down to the molecules absorb heat, and they do it in 4 ways. So imagine that you're a carbon dioxide molecule, so you're carbon with 2 oxygens out here, and or there's lots of water vapor that also is important, and so you could be the oxygen with 2 hydrogens out here, and they do a really simple thing. So everybody raise your hands. Let's make sure everybody knows how molecules absorb heat. So they do their bonds, the bonds that connect, those are your arms that connect the different atoms. They absorb energy. They start getting energized this way. This is called symmetric bond stretching. They also do asymmetric bond stretching. So this, hopefully you're feeling the greenhouse effect warming you up. And they also bend. They bend this way. And if you're really excited, the thing that really absorbs a lot of heat is they start rotating. And you do that at home every day in the microwave. That's how microwaves heat your food is by causing the water molecules to rotate. So that's the basic of the greenhouse effect. And so the big question is, how many of those molecules that get energized are we going to put into the atmosphere in the future? So I'm going to show you a little bit about the future, just picking two possible scenarios, this kind of blue one, where we start to level out the amount of CO2 in the atmosphere, versus the red one where it just runs away from us. I also love talking about this up here because the Tetons landscape is a perfect place to give you some context for the impact of climate change. So if you go up to Jenny Lake or go up into the mountains up the road, you can look at where these glaciers were 20,000 years ago. And the thing that many people may not know is that Jenny Lake was formed by a big glacier. You might know that, but it was formed under a climate that was only about 5 to 7 degrees Fahrenheit cooler than today. So that that might not seem like a tremendous amount of cooler temperatures. It was 5 to 7, roughly 6 degrees Fahrenheit was enough to warm up this region and melt away all those glaciers. All of Yellowstone was covered in big ice cap. That melted away. So just to think about that, here's a photo looking up towards Taggart Lake and up to some of the canyons above it. The landscape up there is covered in these glacial moraines, these big features that were produced by the glaciers. And the canyons are these big U-shaped valleys where the glaciers came down and carved out the mountains. Well, if we go back 20,000 years ago to a world that was roughly 6 degrees Fahrenheit cooler than right now, this was a totally different landscape covered in these big glaciers. I've lost track of where I am with the slides. Okay. So this is roughly what it would have looked like in a world that was 6 degrees cooler. And so about 6 degrees of warming was enough to melt those glaciers away. All of Yellowstone was covered, and it was that completely melted away because of roughly 6 degrees of warming. So keep that massive transformation in your mind. And think about how totally different the Snake River would have been with these glaciers there and all the water flowing downstream. I think it's really useful to have that transformation from the past in mind when we think about how things could change here in the future. So this, hopefully you see the temperature graph here going from 1900 out to 2100, shows like kind of the lots of historic, the black line is the historic changes. This is for this region, not a global picture. This is really for the Snake River region. And it's from, by the way, this is the Greater Yellowstone Climate Assessment that we published in 2021. If you're interested in reading more about this, it's online at gyclimate.org. And I have a few copies if people are interested. But those two scenarios, one where we sort of mitigate the amount of carbon into the atmosphere is the blue possible future, and one where it runs away from us is the red future. And so under the blue scenario, things warm up by about 7 degrees Fahrenheit or so. And under the red scenario, where we really add a lot of carbon to the future, to the atmosphere, temperatures warm up by about 13 degrees Fahrenheit. So again, put that in the context of that 5 to 7 degrees was the difference between the last ice age and today. We're talking about the end of this century, even potentially sort of middle part of this century, being a time period where the amount of transformation of our water resources is similar to what happened over the last 20,000 years. So the magnitude of change here is not trivial. The big thing about it is that we have these choices collectively, globally, before us as to what that future looks like. And that's important because it's not just how warm will it be at the end of the century, it's also how soon will we get to 6 degrees warmer world. Is that going to happen in 2060, because we've put a lot of carbon into the atmosphere, or will it happen in 2100? And that's a 40-year difference, 40 more years to adapt and mitigate and plan. and adjust to it. So buying ourselves some time is potentially a really important value here. On the other side of this, though, is that we're already kind of locked in regardless of what we're doing. The next 30 years or so, it doesn't really matter. We're basically going to see roughly the same changes under either of these scenarios. We're going to certainly see several degrees more of warming. That will be important. And so if you're thinking about building new infrastructure here that's going to last 30 years or so, we actually have fairly good certainty as to how things might play out over that time frame, even if we're quite uncertain further out into the future. So we're only at the beginning of these changes that are taking place. So we're starting to see things. We're starting to have these smoky days from all the wildfires. Jackson Lake was totally drawn down last year. We're starting to see these things. But let's just kind of work through what really has changed here so far. And you might be aware that if you look at the weather station data from Jackson itself, there's not much. If you look at the daytime temperatures over the last 100 years or so, there's not much of an obvious warming trend. If anything, at that weather station over the last couple of decades has actually been pretty cold. But this is a good example of how one spot is not necessarily representative of everywhere and everything that's going on. And also how the changes that we're experiencing are somewhat complicated. It turns out that the sort of cooling possibly happening in Jackson doesn't even apply to Moose. So if you go up to the visitor center at Moose, it's actually different up there. So there are across the region some differences. So that story from Jackson, if you've heard that climate here isn't really changing, well, that's not the whole story. But we could look around at a lot of the other towns in the area. So each of the lines on this graph is showing you how the temperatures have changed over the last 100 years at Moran or over in Driggs or Alta, down in DuBois or Pinedale. And an important thing you'll see here is there's still, if you look at these daytime temperatures, there's not much that has happened. And we're kind of fortunate here. This is actually unusual. This is, I think, possibly going to lead more people to want to come to this place because as other parts of the world get warmer and drier, it's remained relatively stable here in the daytime. It gets different if we look at the nighttime. So hopefully you can see the night graph here. And all of the nighttime temperatures have slowly been ratcheting up. This actually is really important for our water quality because normally at night when it's cold, the water loses heat, and it loses heat out to those nice, clear, dark skies at night. But because we're adding all those molecules up there, absorbing heat, less heat is able to escape from the ground, from the atmosphere, and from our water in the nighttime. And so our cold minimum nighttime temperatures have been going up and up and up. Not as dramatically as some other parts of the world, but still enough that this is something that's possibly transforming our aquatic ecosystems. It's keeping that water a little bit warmer. It's allowing for those algal blooms to really take advantage of the nutrients that are in there. And this is an issue to think about. So overall, hopefully you can see the graph here. That's the average temperatures across all of the Yellowstone region since about 1950. If you average all those together, both the daytime temperatures and the nighttime temperatures across this region have generally gone up by about 2.3 degrees Fahrenheit since 1950. And there's not much reason to think that trend is going to stop. We expect it really to project out, like I was saying earlier. And so this is something that is going to interact in various ways with our water resources. So the biggest change here, sorry, just checking still that I'm on the right slide. The biggest change, the one that really shocked me the most when we were digging into all the data here, is that when you take all the weather stations around the Yellowstone region, that since 1950, there's actually been very little change in total precipitation, but there's been a significant reduction in snowfall. And so it's still wet. it's still a wet place, but back in 1950s, you'd get, on average, across the region, 100 inches or so of snow. Well, that's gone down by about 24 inches over those 70 years. And so it's, 25% reduction. And this is really fundamentally changing how water works here. And September, all this rain we have right now, is a really good example, because in the past, this would be a snowstorm. In fact, there's been a 96% reduction in snow in September, even though the amount of total precipitation hasn't changed. So in the middle of the winter, it might not seem like it's changing much, but on these shoulder seasons, it's really started to come down, and that's making that snow season shorter, and it's affecting how water flows through our rivers. So here, this kind of captures what's transforming how our rivers work. So there's both increasing spring flooding and lower flows, greater summer drought later in the year. So these are just graphs for the Yellowstone River, just as an example. But what they're showing is for each month, the bar is showing what percent deviation is it from the way it had been kind of in the mid-20th century. From 1950 to 1984, what was it like versus the last 30 years or so? And what you can see is that as the snow is melting earlier, we get bigger flows in April, May, and June. It depends on where you are in the river, so there's like two different stations here represented. But all that water, all that snow melt, first off, there's less snow, but it's also running off sooner. And so that means that later in the summer, we have 10% or less water through most of the summer and fall months in the river than we used to. So again, this less water. You have those warmer nights combining with less water. That makes that water warmer, makes it easier. Some of that water is stiller. It makes it easier for algal blooms and things to take place. And so this is a type of transformation in our river systems that we have to keep in mind is going to continue. Now, of course, the Bureau of Reclamation might decide to manage Jackson Lake in a way that affects this, but this is kind of what the natural system is tending towards doing right now. So how will these trends continue in the future? What are some of the ways in which this might play out going forward? And I'll just kind of wrap things up here with giving you two kind of key examples, two things that I think are really significant to keep in mind about where we could be headed in terms of our local climate. So the first is it's easy to hear a lot about kind of the average temperature and how it might change, and that seems very abstract. So I find it easier to think about things like how many days per year are we going to have above 90 degrees Fahrenheit? And in Jackson, of course, that only happens a few times a year. We might wish it would happen right now, but it hasn't. But it doesn't usually happen very much. But on this sort of range of possible futures in terms of the emissions that we put into the atmosphere, with some mitigation of the amount of CO2 that goes in the atmosphere, we expect by mid to late century that we probably could get to the point of having about 2 weeks of 90-degree weather every year. And imagine that also gets combined with some smoke in the air. That may not be our favorite kind of outcome, but it's much worse under the situation where we don't mitigate the amount of carbon to the atmosphere. And under a high emissions scenario, we end up with about 2 months of 90-degree weather by the end of the century. And so you just think about all the possible risks that go along with this. This is much warmer conditions for the water, greater fire risk that has all kinds of consequences with it, plus just the issue that not necessarily all homes in the region have air conditioning, and how does that affect our housing crisis that is important in the area. So these are real transformations, but the one that is most important for water is this move away from snow. The snow is melting. So there's a map here that is kind of is trying to show you where in the winter is most of the region covered in snow. Where is most of the precipitation falling as snow? And so this map is centered. I know it doesn't have the normal political boundaries to help you navigate. The middle of it is Yellowstone National Park, and you might notice the black, thicker line on the outside is the outline of the greater Yellowstone ecosystem. The other black lines are the edges of the different watersheds. So you may recognize the upper Snake River kind of towards the center or bottom there. The blue is all the high country that just is mostly dominated by snow all winter. Red are areas where there's high risk of rain on snow. So we do get some rain events during the winter, and it can fall on the snow, creating some flood risk. But as temperatures creep up, and the maps I'm going to show you here are even for the mitigation scenario, where we manage the amount of carbon emissions to the atmosphere, we start losing this snow-dominated area, and we start having more and more areas have this risk of rain on snow events, and greater and greater portions of the region just dominated by rain, even in midwinter. So, the next 20 years or so, it doesn't look fundamentally different from where we are right now. But by the time we get to mid-century, which shockingly to me isn't that far away, by 2050 or so, we really start pushing the snow-dominated portion of the region up higher. And so in this scenario, the place where you could really count on snow for sure without much rain, it starts to get up to the level of Teton Pass or so. And by the time you get later into the century, by 2060s, 2070s, 2080s, you're starting to get to that, you're only counting on snow above about 10,000 feet. So you're starting to get to the point where the only place you can be guaranteed to get snow is if you take the tram up to the top of the Jackson Hole Mountain Resort. And under the higher emission scenario, this goes faster and it pushes up even higher, where eventually by the late part of the century, you're talking about snow only guaranteed above 13,000 feet. So this is a major transformation in our water supply, and it has to be something to keep in mind in managing and planning for the future. There's all this development issues tied to how we manage our septic systems and things like that, and they're going to interact with these ways in which our water resources are likely to change. So, I'll conclude here by saying, think back to 1942 and try to imagine what it'll look like here in 2042. Our sort of collective global choices about carbon emissions will really be key as to how this will look. And it's worth keeping in mind that we're talking about kind of ice age scale transformation of the landscape in terms of the climate change. So it's not a minor thing, and it really is something where we do better to think about it and plan for it than to ignore it. And of course, water is really a primary concern. So thanks a lot. I really appreciate the chance to share this with you. So I can take any questions for a few minutes here. Okay.
I'd like to begin with your talk. I would say, I like the beginning. This isn't functional. This big echo. There it is. I like the beginning of your talk. It's probably no secret that we have a meteorologist on the newspaper that is a climate change denier. One of his recent articles, which I think was just 2 weeks ago, he said that it was because there were huge volcano actions that we were getting more water in the atmosphere, and that's why we've had higher temperatures for the past couple of years. So I think it's really tough in this county to have such a prevalent voice that's in the newspaper. When he goes to the library and holds a talk on meteorology and climate change, the room is overflowing with people doing hurrahs because he's doing all this. So it's a tough conversation. I'm wondering if you can help us with that.
I've lived in Wyoming long enough to know this is a tough conversation. It is. I'll just come back to the really basic point, which is all the other ideas that people put out there about other things that might cause the climate to change. They're totally worth considering. There's many things that cause climate change, but at the end of the day, carbon dioxide is a really good insulator. It's really good at trapping heat. It does these things as a molecule that absorbs heat. And so any alternative explanation has to account for why adding all of that insulation to the atmosphere isn't also going to make things warmer. I mean, that is the most fundamental part. And we know we're putting it in there. We have pumped a ton of carbon out of the ground. We put it through our cars and our homes and all kinds of things and put it into the atmosphere. We know it's getting there, and we know it's coming from us. And basically, if I take my jacket off, I expect to feel cooler. If I put it on, I expect to feel warmer. Well, we've put on a jacket of carbon dioxide, a jacket of insulation onto the atmosphere. And we've known the physics of how that works since the 1800s. So it's really it's not even remotely a controversy in the scientific world as to why the world is warming. But that doesn't mean that, the last truly cold winter in Wyoming was 1991, and that was because Mount Pinatubo erupted and put a whole bunch of ash into the atmosphere, and it acted to shade the Earth, and it blocked the sunlight reaching the surface. And so for a year, we had an unusually cold winter. But honestly, the state of Wyoming has not had an unusually cold winter since then. So in that case, volcanoes were working the opposite direction. So I'm happy to talk with people more about all those details. But yes, but I know Jackson is a really interesting place where the daytime temperatures are not going up that much, but the nighttime ones are changing, and that matters a lot.
Thank you for being here and for your presentation. My name is Wes Gardner. I'm a county commissioner. I'm curious as to your mitigation scenario. Obviously, we're not in that scenario today.
Yeah.
Can you play out a little bit for us what the next 5, 10, 20 years would look like in order to reach that scenario?
Yeah, I mean, this is a very large challenge. This absolutely involves us fully embracing the energy transition. We are certainly not in any immediate place where we're going to move away from fossil fuels tomorrow. Last year, even though the coal industry has gone down, last year was still the largest year of coal use in the world. So we have to transition, and this will mean things like really moving towards electrification of transportation. But there's a lot of challenges that come with that, and I think this is something that we're going to have to grapple with. I mean, the land use footprint of adding solar and wind enough to really start decreasing that fossil fuel use is tremendous. And so that will have its own conservation consequences that we have to think a lot about. It also involves really truly industrial scale investment in those energy changes. I mean, the rate at which we'd have to build new energy sources is quite high. But it's incumbent on individual communities to decide that that's what we're going to commit to in order to make that happen. I do think I sort of expect that we're not fully going to get to that most extreme outcome because we are making some of those choices, even without real policies in place. Just economically, there's a lot of economic incentive right now to move towards solar and wind because it's actually cheaper in places. I mean, it's amazing to me that even in Texas, there's an example of a coal-fired plant being replaced with solar because it was cheaper for that utility to produce the energy from solar. So I think there's economic forces that will help to move this transition forward, and that keeps me hopeful that we won't get to the most extreme outcome. But I'm not particularly optimistic about the scenarios where we really stop putting in CO2 tomorrow and hold it steady. So I feel like we're somewhere in that intermediate scenario, like the one with some mitigation, is where I feel most likely we're going to end up. But it does involve us continuing to commit to those transitions. I hope that helps.
Quick question. Can you talk about how these changes may impact the availability of our groundwater in the valley?
Oh, yeah.
It's a sole source aquifer. Virtually every drop of our drinking water comes from the Snake River aquifer.
Yes. So the question is about how will these changes impact the aquifer, the groundwater, and of course, the Jackson Hole is a big bucket full of sand basically, and you pour water into that sand, and it stays there, but it likes to flow through there. The way we pour water into that groundwater is by melting snow in the spring. If you just rain the water, it will land on the land surface, get used really quickly by plants, and get evaporated away, and it doesn't go into the groundwater most often. But when you have all that snow melt, it just saturates the ground, and it just overwhelms the ability of evaporation and the plants to take up the water. So that snow melt is so critical to resupplying the groundwater. So this is actually something that's, I think, needs more consideration, is that as we move away from snow, which is quite likely, at least to some degree, that has a strong ability to impact the groundwater levels. And I've been studying the ancient groundwater levels in this region. We actually can go out to a lot of the mountain lakes or lakes like the potholes out here, and you can see that the water levels, which in those ponds are tied into the groundwater level, they've been in the past much lower during times when we know there was less snow in the mountains. So I think there's a real factor to consider that the groundwater supply here could be drawn down in meaningful ways over time.
A quick follow-up, which is the qualitative side of that, which is to say you spoke very briefly about the idea that eutrophication becomes a much bigger problem, and ecological perspective, the economy is based upon being able to utilize our different water and rivers. Can you speak a little bit more to how dramatic that idea of persistent temperature increases in the diurnal cycle ends up representing and really presenting to the public eye in terms of enormous algal blooms and all the degradation that comes with that?
Yeah, it's interesting. One of the things that's like an optimistic story here is you may not be aware of some work that was recently done by one of my colleagues at the University of Wyoming, where she looked at the water quality of lakes all across Wyoming since the 80s using satellite imagery, and impressively, they've really cleaned up. They've become better, and that's the Clean Air Act at work. It actually is having the nitrogen deposition, which was getting to those lakes, has really improved things. The thing that's countering that now is the air temperatures going up, water temperatures going up, and water levels being lower seasonally. And so there's two things I think are worth noting, is that there has been a increase in harmful bacterial blooms, even in alpine settings, where it's not directly affected by septic systems. So you can imagine if you're adding in nutrients, how much more intense that would become. The other thing is that, you think about the other thing that's quite valuable here is our cold water fisheries. The cold water fisheries, really, those fish are quite sensitive to those water temperatures. And you can even just look historically at years where the flows were moderated in a way that the water temperatures changed. There were fluctuations in the trout populations. I'm not sure this is giving the picture that you're thinking of, but there is evidence to support the idea that you sort of end up with these greener waters with less healthy fish populations. And by the way, that groundwater here is really essential to keeping that cold water fishery healthy. It really plays a key role. So I'm not sure if I quite hit what you're aiming for there, but there's certainly this transformation of those ecosystems, and that's something our big project is focused on trying to better understand right now. We're working, our team, that we got this grant from the National Science Foundation to link atmospheric sciences with hydrology, but then with the aquatic ecologists studying the fish and the algal blooms, and then also with economists looking at the economic impact of changing those activities. So stay tuned. That's what we hope to be able to tell you more about in the future. Yeah.
Got to turn it on. There we go. Hey, great talk.
Thanks.
So I've worked in the solar industry for my entire 30-year career, so obviously been really passionate about climate change and thinking about it for a long time. And I thought what was great about your talk is just acknowledging that it's frankly going to be bad. There's not too much we can do to prevent some very serious outcomes. I think for us in Jackson Hole, it's likely, we won't be skiing below the Casper lift. The fishing is going to get really tough, except probably in the tailwaters. So that's big, but of course it could get much worse.
Mm-hmm.
So,
Exactly.
One thing I want to dispel you of is actually there's a lot of hope in renewable energy
Yeah,
right now.
absolutely. Yeah.
Solar photovoltaics now are the cheapest energy source on Earth. 80% of all new electric power generation going in worldwide is solar or wind. So it's definitely happening. Electrification's happening with electric vehicles. So everyone here, I would just encourage you to put solar on your roof, buy electric cars. It's the one thing you can do. I know it doesn't make great economic sense when you're paying 5 cents a kilowatt hour here, but you gotta do it because it's the right thing to do. And then also, it's a political problem. It's so sad that like environmentalism has become a, bipolar political issue in our country. So talk to your Republican friends, explain to them what's happening. We've got to come together as a country. The legislation passed by the Biden administration, the Inflation Reduction Act, is an absolute game changer. That's the most important legislation that's been passed in this country since the Clean Water Act. And so please support that. It's making a difference already today. It's not enough. We clearly need to do more. I agree with you. There's not a lot of scenarios where it starts to go down anytime soon, but we got to avoid the absolute worst case impacts. So it's going to be bad, but it could be much worse.
Yeah, thanks for amplifying that. I totally agree. It's we have this huge choice in front of us in terms of how bad it will be. And I think we still have a lot of opportunity to keep it in a manageable frame and also make it happen more slowly. And so by making it, even if it warms up by a certain amount, by making it happen more slowly, it gives us more time to adjust our infrastructure and adjust our expectations to plan for that. It's so fantastic. It's so optimistic, or I feel optimistic because of the economic change where solar, in particular, has become so economically the right choice to make in many places. I mean, here there's hydropower that's making it cheap already, but I live down in Laramie, and for us down there, solar really wins out really quickly. So it's really a valuable thing to get. It just means that we have to keep working at it. We have to stay on top of that.
And by the way, there's plenty of land.
Yeah.
So NREL's estimated that the amount of area that would have to be covered in photovoltaics to power the entire country is less than the amount of area that's already paved over by interstate highways.
Yeah.
Right?
But
So if you think of it in that kind of a context, it definitely can be done,
Yeah.
especially with rooftop PV. There's lots of roofs that are already out there today.
Well, and the example that was given earlier of how that actually increases sort of resilience, in the case of both, there's examples both from California where communities were impacted by wildfire and communities in Florida where they impacted by hurricanes, where the communities that already had their local distributed solar energy source were much more resilient to those extreme events. And that's something worth keeping in mind here. But it also is not a small challenge. I mean, the amount of area, the good thing about solar is you can put it on most people's roofs, but it still potentially adds up to the area the size of Massachusetts, Connecticut, and Rhode Island in total. But we have to do that, which is the key. The key challenge is keeping that moving. I saw one more hand, but I know we'll take one last question and then transition.
Can you hear me?
Yes.
The New York Times had a long article on the concept of spreading iron on the oceans. Would you comment on that?
Yeah, so there are various ideas of geoengineering our ways out of this, and one idea is you dump a bunch of iron filings into the Southern Ocean, in particular off of Antarctica, and that fertilizes the ocean and takes up a lot of carbon dioxide out of the atmosphere. And we know geologically that this is something that can happen if you add nutrients to the ocean. You can take a lot of carbon dioxide out of the atmosphere. The challenge with some of these things, and they've done experiments, you can actually see, there's a great experiment where they went out to the ocean, they dumped all these iron filings in the Southern Ocean, and you could see in satellite imagery how that created a huge area where algal blooms took place in the ocean and took a lot of carbon dioxide out of the atmosphere. The real problem with a lot of these types of approaches is both the energy cost of doing that. You have to get a lot of iron and grind it up and get it out to the ocean in a way that's effective. But then also the unintended consequences. And so many of these challenges, or many of these ideas are interesting, but just as we're talking about water quality issues here, we don't necessarily want to unduly fertilize portions of the ocean that have big consequences for our fisheries or other things there. So it's, I think it's probably going to end up being all possible options on the table in terms of how we manage this. So I wouldn't be totally surprised if we don't in some way employ methods like that. But I think many of these ideas still need deeper study in terms of what the consequences will be. And that's, and unfortunately, some things that people have thought like this might be hopeful, like certain forestry management practices have turned out not to be quite as effective in the long run as people initially thought. So I'm not speaking much detail to that, but to me, I fear that it's something that would take too much energy to get to the large scale to really keep the carbon levels low, and there are significant ecological consequences we'd have to think through. But it's great to know that there are things we could do that will help even buy us some time to adjust, and that's important. All right, well, thank you very much. I appreciate the chance to chat with you.